Okay.
Okay. So, good morning. And we start today the last subject of the course, which is compact operators. So this is, well, in some sense, well, all the subjects are very important. This is extremely important because a lot of operators are compact. And why we are interested in compact operators? Well, because it's the most, well, is the extension from bounded operators in finite dimensional spaces, which preserves almost all properties, or a lot of properties that we have in finite dimension. So these properties are, for example, but basically what we are interested is, let's say, in the finite dimensional case, so we are in RD, then a linear operator is a matrix. So an operator, let's say, which is linear on RD, in RD is a matrix. Okay? And what we know, well, we know a lot about linear algebra, and in particular, we know, for example, that well, you have the decomposition into eigenvectors and eigenspaces. So, for example, you know that okay, you have the eigenvectors, the eigenvalues. So Ax equal to lambda x, and eigenvectors. Okay. So the aim of this part is to reach something as similar as this guy, but for the case of compact operators. Because if, so what we know, another important result is if A is symmetric, okay, then, okay, you have the base. So you know that this relation here becomes, okay, you define a base of eigenvectors, or you can diagonalize A. Okay, so the aim...
Base, orthonormal base of agent.
Orthonormal, yes, orthonormal base. So we want to, so let me add this orthonormal. So the same can be done for compact operators, which are, well, we can call it symmetric, because here there is no problem. But actually, what you will see in the literature is self-adjoint. Self-adjoint is different than symmetric when the operator unbounded are not bounded, but we will not analyze this case. So the aim of this last lecture is exactly to arrive to the proof, or to show that you have something similar to this structure when the operator is compact. In general, this is not true, so even to give meaning to what is the base of eigenvectors is very complicated, and you have what is called spectral measures, so you have objects more complicated than this one. So let's start now. So definition. So what is compact operator? So the linear operator over a Banach space E is compact when, okay, the image of the unit ball, okay, here I can take even from E to another space, but at the end the analysis will be done, you see, in the same space. So when the unit ball is compact, strongly, pre-compact, so its closure is compact in F. So, so the observation is that in finite dimensional space, every bounded operator is compact, no? While in the infinite dimensional case, well, not every bounded operation is compact. So the example that is very singular or very interesting in this case is this one, the right shift on L2. So define T, which acts on the sequence, let's say xn, and xn is in L2. Okay, so its component k is equal to x k minus 1. And if k is equal to 0, it is 0. So what we do now is the translation, is the right shift, sorry. So essentially, if you have the sequence, k equal to 1, say 1. Depends when you start in 0 or 1. So this is n in the natural number. So I give you the values, and what I do, I just shift by 1. So, okay, and here I say it is 0. So this is clearly non-compact because, okay, you can prove in, well, for example, the image of the unit element, so T of the En is En plus 1, where En is the element which is 0, 1 in the n position, and 0. Okay, so now we have the image of the unit ball contains countably many elements whose distance is 1. Or it is actually square root of 2 because we are in L2. So it's not possible to have that the image is compact. So this operator is non-compact. Okay, so let's do now the first result. So how about compact operators? Theorem. So the set of compact operators KEF is a closed subspace of the linear operator in the strong norm. Okay, which norm I put here? We remember we have many. We put the uniform, the standard one, the uniform norm. So T minus prime is the sup for u equal to 1 of tu minus t prime u norm f. So it's the uniform norm. Okay. So how about the proof, this one? If you remember, we have already considered this setting in several proofs before, because we know that So if Tn converges to T in this norm, then Tn of the unit ball converge, well, to the image of the unit ball uniformly, which means that you can estimate uniformly the distance between this compact set and this limit set, or this pre-compact set. And if you remember, we did, the first time we did it was in the Ascori-Alzera proof, no? Or, well, not in the application of the Ascori-Alzera proof for the Kolmogorov theorem, the strong compactness in LP of sets which are uniformly continuous with respect to translation. And so this gives, so this property here implies that the set is totally bounded. So, which means that for all epsilon, I recall it, for all epsilon greater than 0, there exist finitely many xi such that, okay, this set is covered by the union of the balls in F centered, okay, let's call it yi epsilon. Because the set here is totally bounded, you have the uniform convergence. So, for example, you take epsilon half covering this guy, then you take the distance is epsilon half. So when you increase to epsilon, they are covered by the triangle inequality. Okay, and what about the linearity? Well, the linearity is elementary because the sum of the vector sum of two compact sets is compact. Because you have sequences, okay, here we are in metric spaces, so it's very easy to be done by sequences. Okay, so we discovered that this is a closed compact operator. So let's see a particular class of these operators, which is very important because the way to prove that an operator is compact, the easiest way is to show that it is approximated by compact operators. Okay, well, there are other ways, of course. So, for example, if you know that the image is in a compact subset, well, you are fine. So, in this case, we say that T is of finite rank if the image of E is finite dimensional. Okay, so let's see immediately a corollary of, well, a corollary. But clearly an observation, so remark, T finite rank, then T is compact. Okay? So T is bounded, and then I just come back to the finite dimensional case where balls are compact, so locally compact space. So now we apply this theorem where the approximation sequence is a sequence with finite rank, and we deduce immediately an easy way to say if an operator is compact. So if Tn is finite rank, and Tn converge to T in the uniform topology, then T is compact. Okay, now the discussion is if the opposite hold. There is a discussion about the opposite hold, and so I just say it is a remark. So if F is Hilbert, then the opposite hold. So let me, well, maybe you see already why is that the case. So the fact is that what you do, you use the property that the ball is compact, the image of the ball is pre-compact, so it's totally bound. Take the yi such that T of the ball is contained in the union, the finite union of these yi. Okay? Now what you do, let P, okay, let P over this, let's say F is the projection on F, which is the span of this yi. And now I say T minus pk compose T, the uniform norm is less than, okay, should be epsilon, or 2 epsilon, it's 2 epsilon. Okay, so why is that so? Because well, because I can use the properties of projection. Because T minus pk Tu, okay, there exists one of these yi whose distance is epsilon, so it is Tu minus yi plus yi minus pk Tu. And now the pk over, so pk of yi is equal to yi, because yi is in the span. So what I get is less than, okay, Tu minus yi, pk, okay, Tu minus yi, less or equal. Now I use that in Hilbert space, the projection operator is bounded by 1, is a contraction. Okay, so it is 2 times Tu minus yi, and then I get less than 2 epsilon. So the opposite of the corollary holds in Hilbert spaces, but is not true in general. Okay. What about composition now? These are some elementary stuff. Position. Okay, now I need to state what is let's state one thing. So let's say that T is linear and S is compact. Then S composed T is compact. Okay, which is immediate because the image, so the image of the unit ball is a bounded set, and the image of bounded sets. Okay, this definition is stated for balls, but clearly by linearity it holds also for any bounded set. So the image of a bounded set is pre-compact, and so the image of through this one is pre-compact. And then, okay, you have the other case. And what you use now that for continuous function, the image of compact sets is compact. Okay, in particular, this one is continuous. Okay, so last result in this preliminary part is what about the adjoint? So we did not work a lot about adjoint operators, so I need to introduce it. Because I jumped that part since the book is doing unbounded operators, and this is additional difficulties that well, are not really necessary for the introduction. So definition, we need to know what is an adjoint. So the adjoint is nothing else than the transpose. So I want just to rephrase what is the operation of transposing matrices into an operation on continuous operators. So T is now a linear operator, and now, so how to define the adjoint? So you recall that the adjoint has the property. Okay, let me write. So I want to do, let me write the formula, and then, so I want to say, so if I have a functional f over tu is equal to t star f u. Because this is the finite dimensional case. If you remember, in the finite dimensional case, I have that xt a y is equal to a t x t y. And so if I rephrase from the point of view of Banach spaces, where I cannot identify the dual with the space itself, so now I have that f is in the dual of f, because T of u is in f. This guy is in the dual of E. Yeah, then T star adjoint is the operator in acts from, you see, acts from f star into E star, such that this holds for all f for all u in E, which, just to remember, the formula is only this operation translated into Banach spaces, where the duality is not as elementary as in finite case. Okay, so what's the problem, or what's the main properties of this operator?
Has same norm?
Pardon?
Has same norm is T star.
You want to say that is the estimate of the norm? This is what we wanted to say. Maybe you okay, I had the suggestion if you write in the chat, because sometimes I don't hear very well. And so I think you want the estimate on the norm, you want to say, which is the next one. Is that correct?
Yes, yes.
Yes.
The same norm.
Same norm. Ah, yes, same norm. Okay, so the main property or main observation well, you know that the matrix norm, whatever is the matrix of these two guys, is the same. So the main observation is that the same. So let's see how to estimate the norm. So we know that T star EF U, which is equal to FTU, by definition, is less or equal than norm of T, norm of F, norm of U. So this is in F star, this is E, and this is in the linear EF. So now if we take the supremum with respect to U and then with respect to F, we deduce that the norm of T star, okay, should be less or equal than the norm of T. But actually, if we choose carefully F and Y, you observe that actually, okay, well, we define there exists an F such that this is less than epsilon, and for that F, this object here gives that the norm is greater or equal. This is a good exercise if you want to finish how to make the equality. And just we have to warm up for the exam. Okay, so now when we have this definition in hand, we can talk what if the dual is compact. So indeed it's the case. So how you write it here? Okay, like this. So suppose T is compact, actually is adjoint is compact. So let's see the proof. Just not to confuse. So, okay, we have to prove essentially that for subsequences in the unit ball, okay, let's this direction, subsequences in the unit ball of F star. So up to subsequences, well, a sequence in the unit ball in F star as a subsequence which converges to whose image they converge to some function in F, some vector in F star, in E star, sorry, in E star, in the dual. So the image of the unit ball is compact, so I take subsequent sequence here, up to subsequences, it converges, the images converge to one vector here, okay? So let Vn in the unit ball in F star. Now what we do, and we use Vn T of U is equal to T star Vn U. Okay. And now the trick is the following. So this function, let's call this function, so this function is called this function G over T of U. So G on, let's say, G defined on the closure of the unit ball okay, is a continuous function. Linear function. Why? Because, okay, Vn is a continuous functional, is in the dual of this set. And this set is a compact set. In F.
I think Gn, because G depends on also
So,
N.
moreover, what I have is not only continuous, but also their slope is bounded by 1. So it is also 1 Lipschitz. Why is that so? Because Vn is less or equal than 1. Okay, so if it is less or equal than 1, by definition, the difference between the image is less or equal than their distance. Okay, and then we apply again our Ascoli-Alzera theorem. Ascoli-Alzera theorem. So there exists, which is exactly from that compact, such that G minus Gn in the C0 norm converges to 0. Okay, so let's see what is this G. So this is up to subsequence. Okay, and K. So we take a subsequence and then there exists a subsequent converge. So this means, okay, first of all, I say that G is linear. Why is that so? Because a uniform convergence implies pointwise convergence. So I know that V and K, so Gn, let's say, of this image Y, because let Y belonging to the closure of the ball, so one of this point, and then take another Y prime, and take alpha, beta in R. So now what we know that G and K, or every Gn, Y minus, say, alpha Y, Gn beta Y prime is equal by definition. So everything is linear, so it is alpha here, beta is Gn alpha Y plus beta Y prime. Because, well, you just use the formula here. So the sum you plug in inside, then by linearity, everything goes in. And so now you pass to the limit along this sequence, and the C0 convergence implies the pointwise convergence, so you get that alpha Gy beta Gy prime alpha Y plus beta Y prime. Hence, since it is a continuous functional and it is still 1 Lipschitz, because also this relation passes to the limit, so we say that Gy is represented by some V over Y. And this holds only for Y belonging, well, actually you can extend, but this is only Y, it is the image of the unit ball. Well, it can be extended. Okay, let's say this is it holds in subspace, and then it is represented by a linear function. So it should be that extend by Banach. So now we want to prove that this proves what is the limit. Now we want to pass, this C0 convergence into the convergence of the image. Okay, so we now use the definition of T star. So far what we have just done is that on K, the C0 limit on this compact set, the C0 limit coincide with the linear function. So now I want to show that this linear functional is, it's the image of this linear functional is the image of is the limiting point of the image of this Bn. Okay. So now we use the relation. So what we deduce, so by the C0 convergence, so this goes to P TU, and now by definition this goes to some G U because this is a linear function, no? So this define, so this is less or equal the norm of T, norm of U. So there exists G, which is the limit, at least the weak limit of U. But on the other hand, so what I have that this, now let's go back. P minus Vn Tu. It's equal. Now we represent this guy is G minus T star Vn U. And this guy is less or equal, so tends to 0 uniformly with respect to U. So the supremum with respect to U of this guy goes to 0. Why? Because I have the C0 convergence of the image. So I deduce that the sup over U less than 1 of this scalar product, this duality product, but the supremum of this duality product is this norm B and K. Sorry, I forget there is also K. I take a subsequence. P and K in the in the norm E star tends to 0. Okay, so the conclusion is that, let me review the proof. So you use the Lipschitz, the fact that you can embed the linear functional as one Lipschitz functions on this compact set. Now you just have to look what the uniform convergence means. The uniform convergence means that, the limit is linear, and it means a uniform convergence of this object here by definition of this star, and the uniform convergence of this object here is equal to the convergence in norm. So I have that this star is compact. So how to do the other part? If this star is compact, then T star star is compact from F star star. Hence, the isometric embedding of the image of, well, now what is T star star? So the observation is that T star star, so I'm using two facts here. Use T star star of J composed J is equal to J composed T star T. Why is that so? Okay, you just have to use the definition here. So T star star, now you get T star star, and then you use J, and then you pass it back. And the other fact is that T star star of the ball is compact. So if you sum, you get that 3 compact. T of the ball of, let's say, J composed T of the ball, which is contained because the ball, well, it is this in T star of the ball, because the image through J of the ball of any set, let's say, it's contained in the ball. And then this one is precompact. So we deduce that this closure is precompact, and J being an isometry, get that this guy is compact. There's some computations. So an important observation, so let's conclude with this remark about the weak to strong convergence. So the complex operators are very useful because they allow a passage from weak to strong convergence. So in which setting did I put it? Okay. A remark. If UN weakly converges to U, then TUN strongly converges to TU, if T is compact. Why is that so? Because if you remember, we know that
by the continuity of T, that images converges weakly to TU.
Yeah, we already know that T is continuous with respect to the weak topologies, no? And this implies that TUN weakly converges to TU. Then plus now the compactness, you know that is
strong convergence subsequent zero.
The compactness implies that you take any subsequence which converges should converge to U because the point is uniquely identified. So what about the opposite? So the opposite is true when you have enough points, so enough sequences which converge weakly, no? Because otherwise, there are spaces, if you remember, where weak convergence implies strong convergence, like L1. So, but if it is reflexive, you have enough things. So the converse is true, and this is a nice exercise. If, which one, if E is reflexive.
What do you mean converse?
Yes, that any weakly convergent subsequence has an image which is strongly convergent, then T is compact. So if it is non-compact, you have a sequence which is weakly convergent, but T is not weakly convergent. You need to rule out some cases because if you remember in L1, this implies the strong convergence, and then the criterion is empty. It doesn't say you anything. Okay. So this is about the basic properties of compact operators. Now we are interested into another problem. So I can erase here. This is called the Fredo Alternative, or its freedom theory. So the idea of the whole theory is to give a meaning or extend to Banach spaces the following. So if you want to solve A x equal to y, where A is a matrix, let's say is a square matrix. Okay, so what you know that, well, so y should be in the range of A, and, well, if if x1, x2 are solutions, then, okay, x1 minus x2 belongs to the kernel of A. No, their difference is 0. And moreover, you have the following fact. You have the notion of rank. Of A, which says that, so it says basically that the condition, the number of conditions for y to be in the range of A is equal to the number of conditions for x to be in the kernel. Because the rank tells you that essentially you have a square matrix here, and then you can say 0, 0, and then, okay, 0 here, more or less. So at some point, this is the part that you can solve, and in this coordinate, you have that, well, you cannot say anything about the x here, and y should not be here. And these dimensions are the same. So this is not true in general, no? Because, for example, take an example of the right shift. So we want to solve, let's say, T. T, and then you have the sequence xn is equal to, I have a sequence yn. So it's easy to solve because it says that y1 should be equal to 0 and x n minus 1 should be equal to yn for n greater than 1. So now you have one linear condition, but the kernel of T is equal to 0. So what is called the Fredo Alternative, which tells you that either you can solve this or y should satisfy some number of conditions which is equal to the number of degeneracy of the solution is not true. Okay? So the aim of this part is to prove that, however, when this operator T is the identity minus a compact operator, then we are fine. So we start with this lemma. I think we have seen this lemma many times, but okay. Or at least once before. Or maybe I just use it and I did not express, I don't know, say too much. So the lemma is that, so this lemma is by Ritz. Let E be, okay, here is normal, but that we will stay in Banach. We don't use the complement, but doesn't matter. M is contained in E is a closed subspace. Then, for all epsilon, there exists an U in E such that norm of U is equal to 1 and the distance of U from M is larger than 1 minus epsilon. Okay. So in Banach spaces, or in general Banach spaces is not true, but for reflexive or for sure for Hilbert spaces, we can arrive to the norm 1. For general Banach space, this is not true, but what is sufficient is that this can be as far as almost orthogonal. So this epsilon says that it's almost orthogonal. So for the proof, so just a comment why this is it's important and where we use this property. So this property is because if an operator is compact, and so let me add a remark just to see where we are going. So suppose that E minus T, so suppose T is compact, and let T so let's Ten contained in say T UN. So you have a T. So take the eigenspace E1, which are all the U such that TU is equal to U. So I'm studying the kernel of identity minus T. So the question is what is the dimension of the kernel? Being compact, so if the dimension is infinity, okay, then I construct by this lemma a sequence un such that, well, essentially what happens? Un, the distance from un from the span un minus 1 is larger than 1 minus epsilon. And now we are in trouble. Because, you see, this object here tells you that, this space is non-compact. But on the other hand, if you look in this way, this should be compact. And so I get the fundamental observation that the kernel of this object is finite. Which is, if you go back here, the number of conditions, because there was a problem, how to count uncountably many conditions. But now the number of conditions, when this is identity minus a compact operator, is a natural number, finite number, so it's something which is clear. So this is where we are heading to. So now we do the proof of this guy. The proof of this guy is quite easy because take U not belonging to M. Okay, so, and what you do, you now take B in M, so such that this is almost the projection, so U minus V is larger than D, less than D minus epsilon. D 1 minus epsilon. Which can be done because D being the distance of U from M, there exists a V, so it is the infimum over V U minus V in M. So the infimum, by definition, there exists some point which is as close as we want to the infimum. Now what you do, then take U tilde is U minus V divided by U minus V. So its norm is 1, and then we have only to verify this guy here. Well, this is just U tilde minus V. So this is, this is my minimizer, let's say V bar. So for any data W, it's U over U minus V minus V U minus V minus W. This belongs to M, being a linear subspace. And so by definition, this is, okay, this is U minus some W tilde over U minus V. And, well, if so it is, okay, remember this guy is less than this guy here, so it's less than, and it is greater or equal, this is less than this guy, so it's less than, oh, I get confused, 1 minus epsilon over D. This is greater or equal because I take the lower, U minus W tilde, and this guy is, the minimal one is D. This guy is over epsilon and should be, yes, one over. Okay, that's fine. Okay, so this allows to construct this sequence of vectors to prove that is not is not a compact set, if it is infinite dimensional. So now we have indeed the theorem, which we have seen, if you remember, well, lemma, another lemma by Ritz, which is that if E, okay, I never use the completeness, normite, and B, the unit mole is compact or pre-compact, then, so closure, then E is finite dimensional. And well, and the argument is already stated here, no? So if you have infinitely many, so the proof, the sketch, if UN okay, are such that UN does not belong to the span of the first, then we can, okay, almost orthogonalize it in this sense. We can assume that the distance of UN from this span, let's say this is Mn, is larger than 1/2, for example. So in Hilbert space, when we say the distance is 1, it's exactly the orthogonality relation. So it is just a, let's say, it's an approximation of the orthogonality, of the orthogonal projection. Then UN, okay, cannot be precompact. Unless finite. So cannot be precompact because the distance, there are no convergent subsequences. The distance between UN and the previous one is always 1/2. Because the distance from UN from the span is 1/2. At least 1/2.
Professor, I do not understand that point. Why should they have distance 1?
1/2. I say 1/2.
Half. UN. At least 1/2.
Yeah, so...
No, I mean, why does that imply you
non-compact? Because, so what we do is that, so you take U1, now take U2, such that the distance from U1 from the U2 from the span of U1 is greater than 1/2. And here you use the theorem. Now you know that there exists another point U3. If you finish, it's finite dimensional. Otherwise, you take U3, which does not belong to the span of these two, which is the same as the span of the original one. And then you can assume that U3, the span, U2, 1/2. And then you go on. So you have the property that UN from the span of the previous one is 1/2. Now, this sequence cannot have any convergent subsequence. Because if you have a subsequence which is converging, then the distance at some point is less than 1/2. But if I take, so U1 as a distance between the span, it means in particular that U3, for example, has distance at least 1/2 from U1, because it has distance 1/2 from the linear span of the vectors. Then I say also, okay, remember, I forgot to say that the norm of this guy is equal to 1, we say. Can go to 0, otherwise I cannot assume this thing. So the unit ball, if I have countably many linear independent vectors is not compact, not strongly compact at least. So the only possibility left is that I have only finitely many of them, and in that case is clearly compact because RD is a locally compact space. Is it clear now?
Yes, Professor.
Okay, I don't know if you have time to see the main theorem here. So we will start, and probably we will take it again from the next lecture, because this is the main result. It's what is called the Fredo Alternative. So we have a compact operator, so let, now the notation is K is a compact operator from on itself, because I want to discuss about is identity minus K. Then A, the kernel of identity minus K, sorry, here there is a mismatch the notation, so let's say this is T. Identity minus T is finite dimension. And this is the sketch that I show more or less here, which is more or less this sketch here. Part B. So now we have some general properties on operators whose range or is closed or the kernel is closed. Okay, we will discuss a little bit later. Because this orthogonality relation, I decided not to do them as in the book, because the book does it for unbounded operators. I want to avoid the unbounded operators. So we decided here just to stick with bounded, and then probably we will have a digression on this. So the range of identity minus T is closed, and it holds the range of identity minus T is equal to the kernel identity minus T perpendicular. Then we will see a little bit better. Maybe today we have a digression on this observation here. See if the kernel of identity minus T is equal to 0, then the range of identity minus T is equal to E. And this is, you see, like in the finite dimensional cases, no? So you see, this is exactly, in some sense, the finite dimension. The number of conditions to be inside the range is equal to the, and actually it is the orthogonal, it should be the orthogonal of the kernel. And D, the dimension of the kernel of identity minus T is equal to the dimension of the kernel of identity minus T star.
Professor,
Yeah.
it says here in the book that it should be kernel I minus T star, and
Yes, but of course, because the orthogonality relation is always given in the duality. Yes, is like this. T minus T star. Okay, so maybe So the part A is easy, and then we see immediately, and then we discuss a little bit about this relation here. Okay? So part A. Part A is already in that part there, no? Because the kernel of identity minus T is are all the, by definition, all the U such that TU is equal to U. So what happened is that
Supposing on contradiction, for example. Yes.
yeah. Because
the method of freeze them just do like
that. Because I see just some notes. Okay, so if so, let's do.
Suppose that infinite.
Yeah. So sorry, I
we can pass another sequence.
It's not written very well.
And that sequence is satisfies the condition.
Yeah. So if it is if infinite dimensional, okay, then we find a sequence as in the Ritz theorem. So we have a sequence such that their distance is 1/2. Okay. And but T of UN of the sequence is pre-compact, which is a contradiction because the sequence that I built here is non-pre-compact, while this is pre-compact because T is compact. I'm sorry, I just get stuck for a stupid thing, I don't know, because I was confused on what it was written here. So let's now do the second part. So the part B is more complicated, and I want first to discuss about this orthogonality relation here. Okay, and then we do the proof later, because some part is automatic. I had to put somewhere, I don't remember where I put it, sorry. Okay, so let's talk about orthogonality now. So remember, so if A is a subspace of E, then the orthogonal of A are all the F in the dual, such that F U equal to 0 for all U in A. And vice versa, if A star is a subspace in E star, then A star orthogonal are all the U in E such that F U is equal to 0 for all F in A star. So the first remark is that these two objects are closed. So A orthogonal, A star orthogonal are closed, because they are intersection of closed subspace. So here are, well, this is a weak star closed, and this is weak closed. So, particularly, they are closed. Now we want to see, so now the aim is to relate some objects when through the relation, let's say, we want to relate those objects through T star F U is equal to F TU. Okay. So you see that I have a relation between the scalar product, and then I want to use this orthogonality relation to relate, for example, the kernels. So let's start with something easy here. Let's compute the range of A orthogonal. So what is the definition? So these are, by definition, are all the U. Sorry, these are all the range of A star orthogonal. Sorry, range of T star orthogonal. I don't know why I call it this way. So by definition, these are all the U such that F U is equal to 0 for all F belonging to the range of T star. But then it means that F, so F is the image of some G. So I'll use that T star G U is equal to 0 for all G in E star. Because by definition, if F is in the range, F is equal to T star G. But now this is equal to that guy. So this is equal to the U such that G TU is equal to 0 for all G. Okay, but now since it is equal for all G, this is equal to the U, such that since we are in the dual, TU equal to 0, and then we discover that this is the kernel of a T. So first relation. The range of T star is the kernel of T. Now let's do the other one. So basically, we are trying to say that we are trying to arrive to the point B for general operators, not for operators with a particular property, because you see that from this observation, one necessary condition is that this guy is closed, and this is in the assumption. So I want to show that the property B is complete. I mean, the second part is trivial, or is a consequence of more general facts. And the point B, the only point you have to prove is that the range is common. Okay, let's do this guy here. So now, 2 range of T orthogonal. Okay, the thing is the same. So these are all F in E star, such that F, let's say F V is equal to 0 for all V belonging to the range of A, of T. Okay. So if this is the range, V is TU for some U. So RDF is star such that F TU is equal to 0 for all U in E. Well, now we use the duality here, I mean the definition of adjoint, E star such that T star F U equal to 0 for all U in E. But this is for all U in E, so it means this should be equal to 0. Okay? And so we discover that this is equal to the kernel of T star. Okay, very well. Now let's do the difficult part. I don't know if I have time, but we can start. So, okay, we can cancel the definition. So let's start with the kernel of T orthogonal. Okay, by definition, this is what? These are all the F such that Fu is equal to 0 for all U in the kernel of T. So now assume that F is equal to T star G, so F is in the range of T star. Then I apply the duality relation. So T star, then F U, T star G U, G T U, but this is in the kernel is equal to 0. So what I discover is that this contains the range of T star, and actually contains the range of T star closed. Well, now what is the technique if I want to prove that they coincide? Well, would be that, so now we know that there exists psi and the B dual separating, let's say, the kernel, okay, if the kernel is not 0, let's say separating the range of T star from F bar belonging to the kernel of T perpendicular minus the range of T star closed. But this is not a nu here. But psi does not belong to the J of E. And then we cannot proceed with inequality because what you know is you deduce from this observation is that the weak star closure of this object is the kernel of T orthogonal, but not the weak closure, hence not the strong closure. So the last relation instead is when, I think I will use just 5 minutes, so we will not come back to these orthogonality relations. So let me just observe that So in the book is difficult because they take operators which are unbounded and densely defined, so you can do the theory, but you have to be a little bit more careful. But for the case of bounded operators, you see all the things is quite straightforward with the definition. No, well, you have just to play a little bit, but it's not so, I don't find them particularly complicated. So point 4. Now we consider the opposite, the kernel of A star, perpendicular, equal, definition. These are all the U, such that f u is equal to 0 for all f belonging to the kernel of A star. Sorry, it was T. So now let's repeat the observation. Assume that U is TV, so which means U is in the range of T. Then same computation. FU FTV equal to T star FV equal to 0 because F is in the kernel. So I discover that this contains the range of T and also the closure. So if there exists V tilde, say V bar, belonging to the kernel of T star orthogonal, but not in the closure of the range, then there exists F such that F on the range is 0, on the range of T is 0, but F is different than 0. And F, okay, F is different than 0, and F over V bar is greater than 0, doesn't matter. This is the real condition. Okay, let's consider this guy. This means that F TV is equal to 0, but on the other hand, this is equal to T star FV. So it's 0 for each V. And then this implies, by definition, T star F equal to 0, and so I deduce that okay, F is in the kernel, and then is a contradiction because F cannot be in the kernel. Because V is a point in the kernel orthogonal, and then F V bar is equal to 0. Okay, so we discover that actually this guy is an equality. So now if we go back, if the range is closed, well, it coincides with the kernel orthogonal. Okay, so this is, we finish here. So next time, we conclude the proof with the last 3 points, and we will do what is nice properties for compact self-adjoint operators. And that's it.
Thank you, Professor.
Pardon?
Thank you.
Well.
Thank you.